everyone, thank you so much for coming to this video. So today we're going to be going over differentiation for some specific functions. So please review the lesson that we did on the differentiation as that will come really useful for this lesson. So the learning objectives for today is to be able to differentiate e to the power of kx and a to the power of kx, to be able to differentiate sine kx, cos kx and tan kx, and to be able to differentiate ln x. So we're going to be going over the theory and then doing some practice questions just to make sure you fully understand everything we've done. So like always, there's going to be timestamps in the description of the video, so feel free to skip to any parts you want to. But let's get started. So if we start with the derivative of a to the power of x, you just need to know that the derivative is just equal to a to the power of x times ln a. So if we try and prove this, we can do this by rewriting a to the power of x. So we could say that d over dx of a to the power of x, that's just equal to d over dx of e to the power of ln a to the power of x. So if you remember, if you do e and then raise that to the power of, so if you do the exponential of ln something, you would just get what that is. So if you do e, if you do the if you do e to the power of ln ax, you would just get a to the power of x. So we can rewrite that, and then we can say that's equal to d over dx of e to the power of x ln a, just using the fact that you can bring your power down using log rules. So now we can solve this using chain rules. So we can say that y is equal to e to the u. That means dy over du is equal to e to the power of u, and our u is just x ln a. And then if you do du over dx, you just get, because this is ln a, we can just treat that as a constant. So if that's raised to the power of 1, if you times, sorry, our x is raised to the power of 1, so if you do 1 times ln a, that you just get ln a, and then if you do 1 minus 1, you just get x to the power of 0, which is just 1, so you get that's equal to ln a. So then you can rewrite that, the derivative of that, that's just equal to e to the power of x ln a times ln a. And then if you remember, we can rewrite this term as just e to the power of ln a to the power of x times ln a. And then if you remember that if you do the exponential of ln something, you just get left with a to the power of x. So that would just be equal to a to the power of x of times ln a, and that's your derivative. So that's all you need to really know about a to the power of x and how to find the derivative. You don't necessarily need the proof unless you're asked for it, but just remember this formula here, that derivative is just equal to a to the power of x times ln a. And then if you want to think about e to the power of like x or e to the power of kx, if you remember that e to the power of x, that's just another form of exponential, but instead your a is just e. So then if you were to do the derivative d of dx of e to the power of x using this formula, that would just be equal to e to the power of x ln e. And then if you remember that if you just do ln of e, that's just equal to 1. So therefore this is just equal to e to the power of x. And that's why, if you remember what we did when we were differentiating e to the power of x, we just got that the differential of the derivative of e to the power of x is just itself, e to the power of x. So that's just an overview of how to differentiate e to the power of x and a to the power of x. Just remember that e to the power of x is just a special form of a to the power of x. And if you want more rules of differentiating e to the power of x, then make sure you go back to that video where we were doing it. But let's try some questions on differentiating this. Okay, so we have a question here. We want to differentiate y equals 3 to the power of minus 2x. So feel free to pause the video and try it out for yourself. So the first thing we can do is we can recognize that we could solve this using the chain rule if we just rewrite this as y is equal to 3 to the power of u, and then ru is just minus 2x. So if you think about here using this formula, our a would just be 3, and then our power x is just u, and then we've just subbed in u as minus 2x. So now if we differentiate each of them, we get, if we do dy over du, we just use this formula, so we just get 3 to the power of u ln 3. Then if we do du over dx, that would just be equal to minus 2. So now if you remember from the chain rule that dy over dx, that's just equal to dy over du times du over dx. These would cancel. So if you just multiply them together, you get 3 to the power of u ln 3 times minus 2. And then if we were to simplify this and plug in our u as minus 2x, we get that's equal to minus 2 times 3 to the power of minus 2x ln 3. And that's our answer. We can just rewrite that with brackets as 3 to the power of minus 2x ln 3. So that's our answer to this question. So the key was just recognizing that you can use the chain rule by calling this minus 2x as u, and then we can just use our normal formula that we got for the derivative of a to the power of x. So now that we've been able to differentiate e to the power of x and a to the power of x, let's move on to differentiating our sine x, cos x, and tan x. So we have our each of our trig functions and their derivatives here. So we have if y equals cos x, then dy over dx is just minus sine x. And similarly, if you have y equals cos kx, your dy over dx is just minus k sine kx. Then if you have y equals sine x, your dy over dx is just cos x. And then similarly, if you have y equals sine kx, and you just bring your k out, so you'd have dy over dx is just equal to k sine, this should be cos k sine cos kx. Then if you have y equals tan x, then your dy over dx is just sec squared x. Similarly, if you have y equals tan kx, your dy over dx is just k sec squared kx. So you'd get your formula for this tan x, the derivative of tan x, in your formula booklet. So don't remember if you can't remember that, but you do need to memorize your derivative for cos x and sine x. But if you refer back to your to our video from differentiation from first principles, you can see that we derived these answers using differentiation from first principles. So if I just talk you through quickly how we can also get tan x, the derivative, if in case you've forgotten that for some reason or you can't find it, if they may ask you to prove this as well. So what you do is you remember that if you have y equals tan x, remember that using the identity, that's just is the same as sine x over cos x. And now we can use the quotient rule, if you remember, to work this out. So you'd have u is equal to sine x, and you have b is equal to cos x. Then you can just do du over dx, that's just equal to cos x. And you have your dv over dx, that would just be equal to minus sine x. And then if you would do dy over dx, if you remember the quotient rule, that would just be equal to cos squared x minus sine squared x, so plus sine squared x over this v squared, so that's just over cos squared x. Then if you remember the identity for cos squared x plus sine squared x, that's just equal to 1 over cos squared x. And then if you remember from the reciprocal trig, functions that y 1 over cos squared x, that's just equal to sec squared x. And that's how you get your derivative of tan x. So you're just using the identity of that tan x is equal to sine x over cos x, and then as long as you remember what the derivatives of cos and sine are, you can just use the quotient rule to derive this as sec squared x. And then finally, for these equations with like cos kx, to get that, you just use the equation. You just use the chain rule. So let's say you have y equals cos kx, then you can just say your y is equal to cos u, and then your u is just equal to kx. So then if we were to do dy over du, that would just be equal to minus sine u using here. And then if we have du over dx, that would just be equal to k. So then if we were to do dy over dx, we just multiply the two together. So we just get minus k sine u, and our u is just kx. So that's how we got all these expressions here for the cos kx. And if you were to do the same, you can just try it yourself. For sine kx and tan kx, you should get the same response. So that's just an overview of all the trigonometry derivatives that you need to know. So let's just try some practice questions just to make sure you fully understand how to use them. So we have a practice question here. We have f of x is equal to e cos x, e to the power of cos x, and we want to find the derivative. We want to find f dash x. So feel free to pause the video and try it out for yourself. So this is a combination of our trig derivatives and also our derivative of e to the power of x. But the first thing you want to know is you have two separate functions. So you want to use the chain rule. So we can write y is e to the power of u, with our u being cos x. So then if we do dy over du, using the fact that the derivative of e to the power of u, that would just be itself, e to the power of u. Then if we do du over dx, that's just equal to here, we have that's just equal to minus sine x. So then if we were to multiply them both together, we would get f dash of x is just equal to e to the power of u times minus sine x, multiplying them both together, dy over du times du over dx. And then if you just sub in your u as cos x, that would just be equal to minus sine x e to the power of cos x. So that's just your answer to this question. The key here again was just to recognize that because you have two separate functions, you want to use the chain rule, and then you can just use your derivatives that you know for your trig functions and for your exponential function. So now that we've gone over differentiating sine kx, cos kx, and tan kx, let's move on to differentiating ln x.